What happens when the memory of billions of searches stops serving one gatekeeper? On July 16th, the EU ordered Google to share certain anonymized query and click data with rival search providers. And here's my read on this. Much like the internet itself, search data is too valuable to lock to any single company's exclusive advantage. And yesterday, the EU court agreed. No answer engine gets exclusive access nor final say. Come with me, let's get into it. The European Commission issued two binding decisions. They changed Google's control over search and over Android. These decisions came through the Digital Markets Act. That's the EU law for powerful platform gatekeepers, and these decisions do carry real legal force. The first decision reaches into the machinery behind Google search. Google must share query and click data with rival services for a reasonable fee. That data records what people ask for. It also records which results satisfy them. Every search leaves behind a tiny piece of evidence about our behavior. Billions of searches turn those pieces into an extraordinary map of human attention. Google has built that map across decades of queries. When new AI assistants enter the market, they don't have anything comparable to that. And under the EU decision, that assistant now can license that signal. It can compete through the answers that it provides. It won't have to rebuild Google's entire history first. And the Commission explicitly included AI assistants in its definition of search services, right as search is moving toward conversational answers. So the page of ranked links remains really important, but more and more, the front door is an assistant that reads the web and responds directly. The data sharing rule begins in January 2027. The second decision reaches Android. Google must let competing AI assistants become the default. They must also get the same system hooks available to Google's assistant. That deadline is July 2027. So a rival can gain access at two levels. It can learn from the signal about our behavior around search, and it can also sit at the center of an Android phone. Google framed these decisions as threats to privacy and security, and its legal leadership also raised concerns about trade secrets and possible service degradation. Those are Google's claims about a decision that weakens its most valuable advantage. Privacy and security still do need serious safeguards, of course, but the company that benefits from exclusive access can't treat that exclusive access as the safeguard. And the Commission first pushed for Android to work with rival services in April. The United Kingdom has also imposed opt-out rules around the search gateway. Brussels has now moved beyond early pressure and has set requirements and dates. The January deadline will give us the first full useful measure here. Count how many companies apply for access. A long applicant line would tell us that something is important here. Developers had ideas for better answers, and they were waiting for a path to the data. Search has built up a vast memory. Now that memory is becoming a shared input that more than one assistant can build on. All right, shifting over to a story about a medical breakthrough. Keith Thomas regained arm movement and touch after 6 years of paralysis. Thomas broke his neck in a driving accident. He couldn't move or feel anything from the chest down. Researchers at the Feinstein Institutes built what they call a double neural bypass. Surgeons placed 5 electrode arrays in the brain regions that control movement and touch. When Thomas intends to move, an AI system reads that intent. It decodes the signal and routes it around the damaged sections of his spinal cord. Simulators then activate muscles in his arm and hand. And the bypass also runs in reverse. Signals from his fingertips travel back toward the brain and create a sense of touch. That two-way communication connection is the double in double neural bypass. Motor commands travel out, sensation travels back. Thomas trained with these systems for 35 weeks. His right arm strength increased 86% and his left arm strength rose 62%. Nature Medicine published the work. Those numbers alone would make this a significant case report. But then, a fire near the lab interrupted the experiment, and the fire forced researchers to halt stimulation sessions for 3 months. They expected Thomas's recovered function to fade, but it held. More than 2 years after the implant went in, Thomas still shows measurable gains when researchers switched off the entire system. Okay, that changes what the bypass means. A conventional interface can replace a missing connection while the hardware stays active. But this system appears to have changed Thomas's nervous system through repeated teamwork. His brain kept producing intent. The AI kept translating it. His nerves and muscles kept receiving useful signals. And over time, dormant or partial biological pathways appear to have grown stronger. Now, scientists call that process neuroplasticity. The nervous system strengthens pathways through repeated activity. Neuroscientists Sergei Stavitsky and Charles Greenspan point to neuroplasticity as the likely source of the lasting gains. But I want to keep the scale honest, of course. This is one participant. It's a case report. Greenspan says that researchers need to see the lasting effect in many more people before they can actually call it a reliable therapy, and that makes sense. The treatment also requires brain surgery. It uses multiple electrode arrays and takes months of supervised training. People living with paralysis can't routinely get this treatment tomorrow. The study shows what the system can do and how it might work, but even so, the goal of the entire field has moved with this. A neural interface could help rebuild how the body works. The person may then keep some of that recovery with less help from the electronics over time. That creates an entirely different relationship between a patient and an implanted intelligence system. The system becomes a training partner for living tissue. Its most important effect may be what the body learns to carry forward. And for Keith Thomas, the lasting result was simple. Movement remained even when the switch was off. All right, shifting away from one medical story about a brain implant to another medical story about CRISPR. Jennifer Doudna's lab has designed synthetic CRISPR enzymes. Some edited human genes more efficiently than their natural ancestors. Doudna shared the Nobel Prize for CRISPR, and Science published her lab's latest work here on July 16th. CRISPR began initially as a microbial defense system that bacteria evolved from molecular machines that recognize genetic sequences and cut them. Researchers learned to find those machines in nature, and then they adapted them to edit genes. Doudna's team this time took another route. They worked with AI to design enzymes that don't exist in any organism. The team focused on TNPB proteins. Those are small ancestral nucleases. Scientists think that the much larger Cas12 editors evolved from them. And their small size is the appeal because getting an editor into cells remains one of gene editing's hardest problems. The vehicles that carry an editor into cells have strict size limits. So think of a carry-on bag with a hard frame around it type of thing. A smaller editor leaves more room for the other biological instructions that are needed for the trip. The AI system learned the protein's shapes and evolutionary histories. It also modeled how each enzyme changes shape as it grips and cuts the DNA, and then it proposed entirely new sequences. Several synthetic variants edited human genes more effectively than the natural TNPB proteins that they came from, and that is a striking result. Evolution had billions of years to explore those proteins. Evolution also had to meet countless demands unrelated to human medicine. A designed enzyme can focus on the job that researchers actually need. A companion science paper pushed the size question even further. That team stripped RNA-guided nucleases down toward their smallest working core. Again, the need to deliver the editor drove the work. Søren Leenkamp described the new workflow this way. A model proposes the function. Researchers at the bench test whether the molecule performs it. That changes the wet lab's role. Scientists can spend less time searching nature's catalog, and they can spend more time checking candidates designed for a specific purpose. The July 13th Century Report documented a related result. A generative model worked with a photonic quantum computer to design peptides. You might remember that. Those peptides later bound their targets in lab tests. The strongest gains appeared where earlier training data was scarce. This CRISPR work brings the same design and test approach into gene editing. And the caveat is real, of course. These new enzymes have edited cells in a laboratory. Researchers still face years of tests to check accuracy and safety before this work can actually reach a clinical trial. And then clinical trials have to show that an editor helps new patients without causing unacceptable harm. No patient is receiving one of these synthetic nucleases today, but what the team has shown is narrower, and it's still remarkable. AI can model how a molecular machine moves and create a better candidate. Gene editing's menu just grew beyond the enzymes that evolution happened to leave us. All right, shifting over to energy now. Federal energy regulators directed NERC on July 16th to develop mandatory reliability standards for large data centers and other computational loads. The Federal Energy Regulatory Commission told the North American Electrical Reliability Corporation to write those standards. So FERC regulates major parts of the power system, while NERC writes and enforces the grid's reliability rules. The order uses the phrase computational loads, and that language covers AI data centers and crypto mines as well. The first filing is due on December 31st. A broader plan follows by March 2027. Data centers could then register as entities with direct responsibility for keeping the grid reliable. Power plants have carried that kind of responsibility for years, as you know. The largest computing facilities have generally remained on the customer side of that particular ledger. But their behavior can affect far more than their own electricity bill, which is, of course, one of the big reasons we have so much resistance to these data centers. In July 2024, roughly 1,500 megawatts of data center demand disappeared almost simultaneously from the Eastern Interconnection. Texas recorded 26 separate incidents between 2023 and 2025. Facilities suddenly dropped between 17 and 95% of their demand. These changes happened within milliseconds of grid faults. A data center switching off sounds helpful during a shortage, but when a massive load just vanishes without coordination, it can throw the system completely out of balance. FERC's chair framed the goal as winning the AI race in a way that does not threaten reliability. Now, that statement gives us the agency's preferred frame, and the grid events show why the regulators are acting. But now add PJM. PJM runs the largest power market in the U.S. It serves around 67 million people across 13 states and Washington, D.C. And through its capacity auction, PJM pays generators to guarantee that they'll supply electricity in the future. The auction for 2028 and 2029 is reaching its ceiling of $325 per megawatt day. That is the third consecutive auction at the price cap. And the auction cleared $16.4 billion and still came up 6.8 gigawatts short. Only 525 megawatts of new supply appeared. Ordinary customers pay that price through their electricity bills. Businesses with large power needs pay it too. A 10-megawatt industrial customer paid around $6,000 per month in capacity charges during 2024. And by 2028, that monthly charge moves towards $70,000. One analyst called the market an intervention doom loop. PJM stakeholders have now approved a backstop to keep the grid reliable. It requires data centers to fund new generators directly through 15-year contracts. That shifts the financial risk toward the large load and, of course, its investors. Virginia regulators are considering the same logic for transmission. They weighed a but-for test, which is covering $1.5 billion in spending. The test asks whether those grid upgrades would exist without the new mega users. So a state staff attorney described the current arrangement as glaring cross-class subsidization, and he also pointed to 4 mega users that signed a ratepayer protection pledge in March. And Oregon moved first on another piece of this as well. Its Power Act led regulators to approve Portland General Electric rate changes, raising data center electricity rates around 29% and cutting residential bills by up to 2.1%. Now, for the full timeline of this arc, the ARCS tracker has the complete record. The pressure pushing the other way remains enormous, though. XAI bought a $1 billion gas turbine fleet. Meta's Hyperion expansion targets 5 gigawatts. The largest projects are going up faster than officials can lock these accounting rules into place. Still, the rules are moving in a new direction. When data centers register, they take responsibility. Contracts make them cover the cost. The but-for test links an upgrade to the customer that caused it. The biggest new loads are starting to pay for the grid they require. All right, let's shift over to our last story for today. Inclusion AI scaled label-free reinforcement learning to a 1 trillion parameter open-weight model. Inclusion AI is Ant Group's open-source research arm. It calls its model Ring Zero. The Ring Zero paper is now on Arxiv. You can check it out yourself. The team describes this as the first successful Zero-RL run at 1 trillion parameters. Zero-RL begins with a raw base model. The system earns rewards for successful outcomes without human-labeled examples of good reasoning, which is, by the way, what Claude and ChatGPT and all of the other models really depend on, is that human reinforcement loop. in order to become a good conversational agent with a human. This approach removes much of that handwritten structure that is used in the conventional reasoning training. Ring Zero uses a mixture of experts' design. Between 50 billion and 63 billion parameters activate for each of the tokens, and that makes it possible to run a model with 1 trillion total parameters. Training runs at this scale can collapse easily. Inclusion AI says a 3-part method kept Ring Zero stable and learning. Then 5 behaviors appeared without anyone directly engineering them. The model began checking its own answers. It explored several reasoning paths at once. It developed structured formatting and narrative framing. The 5th behavior has the memorable name context anxiety. Ring Zero tracked how much room remained in its context window, and it adjusted how deeply it reasoned to fit the available space. The model was budgeting its resources as it worked toward a reward. The evidence gives us no reason to say that it was scheming or trying to preserve itself or anything like that. Any capable reasoner working inside a finite workspace benefits from checking how much room remains. It just naturally figured that out. Humans do a version of this during an exam, for example. You answer differently with 2 hours of time left than with 2 minutes left. The model found that strategy through reward alone. Inclusion AI split the training into 2 stages called discovery and sharpening. Useful behaviors appeared first, and later training made them more reliable. The team reports an 84.2% score on a difficult 2026 mathematics exam after the first stage alone. A later MIT-licensed version reportedly scored higher. Now, every benchmark figure does come from the team behind the model itself, so independent researchers still need to reproduce the results. They can do that because Inclusion AI released the weights. So researchers outside the organization can now inspect the model, and they can test the claimed behaviors and see how well the training method holds up. This is another result that supports AI's bitter lesson, that general methods that scale with computing power tend to beat elaborate systems built from human-only knowledge. Ring Zero brings that principle into a new setting, a raw model learned from outcomes at 1 trillion parameter scale. A trillion parameter reasoner learned to manage its own thinking without human examples, and the weights are open for anyone to check out. All right, let's bring this to a close. Search looked like one of the safest places for a built-up advantage to stay permanent. Every query added another clue about what people wanted. Every click made the answering system a little bit better. That feedback loop favored the company that already held the largest history. The EU has now changed what that history can become. Google collected the signal. Rival AI assistants will now be able to license it. That reaches beyond the contest among search companies. The way that we reach knowledge is changing. More and more, we begin with a request and receive a composed, generated answer in the moment. The system at that entrance decides which sources rise to the surface, and it shapes which possibilities appear first. When the underlying signal opens up, more assistants get a chance to earn that position, and today's deeper lesson reaches beyond just search. Generative systems keep expanding the range of possible answers. Biology can learn from an electronic connection. Protein design can move beyond nature's catalog. A raw model can discover how to budget its own reasoning. Public rules can shift the physical costs of building all that intelligence. The old setup depended on scarce inputs staying locked in place. Today's evidence shows those inputs moving. Some become available to license, others become spaces where people can design, others become abilities that an open model shares with the field. Your search begins with a private question. The answer layer is becoming a place where many intelligences can build. The future of search looks like many assistants learning from a shared signal and earning your trust, one answer at a time. We'll see you tomorrow.